So the next speaker will be Andrzej Görlich on the impact of matter fields on quantum geometry.
I'd like to discuss the effect of matter fields on quantum geometry in an approach called causal Demka triangulations. So I will start with a very short introduction. What it is. Causal Demka triangulations is a background-independent and deformatism invariant and also non-perturbative approach to quantum gravity, and it provides a lattice regularization of the formal gravitational path integral. So it replaces it with a sum over triangulations. They are four-dimensional and built of four simplices, which are generalizations of triangles to higher dimensions. And there are some assumptions, like we introduce global proper time foliation. It's a discrete model, so we enumerate slices with integer times. And this allows us also to define an observable volume profile, which is the volume of a slice defined as the number of tetrahedra in this slice. And we also control the topology both of the spatial slices and the global topology. And we can use Monte Carlo techniques because of the foliation. The weak rotation is well defined, and we end up with a statistical model. And we use Monte Carlo techniques to generate configurations according to this probability, and we can measure expectation values of some observables, the one that I mentioned, or study the properties of typical configurations. Even though our building blocks are four-dimensional, the triangulation or a geometry that it represents is nothing like a regular smooth geometry. Here I will focus on a toroidal topology, and it looks much more fractal, more like this picture that is just a visualization illustration on the right-hand side. And now we introduce dynamical scalar fields. Dynamical, it means that they back react on the geometry. So we add the action for the scalar fields to the action that is used to generate those configurations. And we'll take a free massless scalar field. But those scalar fields, they will take values on a circle with circumference delta. And this circumference is a quite important parameter here. And we require that a given scalar field winds exactly once around the circle in given direction, depending how we define it. And we use a discretized version of this action. It consists of a quantum part and a classical part. This may be more technical, but we see that the classical part scales as delta squared in the action. So this suggests that when the circumference grows, the effect of the matter fields will also grow. And we'll start our discussion with just a single dynamical field that winds once around the target space when we go along a non-contractible loop in the time direction. And we can see that for small volumes, for small circumferences, delta, there is no change. And if we look at the volume profile, so the average number of tetrahedra in given slice, there is a drastic change when we cross some value of this delta. We get the cosine function of this volume profile, and it's a pinched profile in the sense that it goes to zero, almost to zero, because it's not possible to go exactly to zero because of discreteness, almost to zero at some points. And in this region, the field changes abruptly as much as possible, while here it is changing slower. This will be also visible later. Now, we can explain this cosine behavior very well with the mystery space model, where we assume spatial homogeneity and isotropy, both of the metric and the scalar field. And one of the solutions is a cosine function for the volume profile, and it works very well. So if we have a single field, there's a pinching in the direction in which the field winds. Now we'll go to more fields, but let me make some introduction for the pictures I will show later. So as I said, the action that we use that govern the fluctuations of this scalar field, it consists of a quantum part and a classical part. And the quantum part can be integrated out. L is the Laplacian, discrete Laplacian for this triangulation, and it's basically negligible. But the classical part, so the field fluctuates around a classical solution, and the classical part is the value of the action for this classical solution that winds also around the circle of circumference delta. And that if we take the dependence on delta in front of this parameter here, this classical part of the action, it depends as delta squared times a function that depends on the triangulation. And if this part becomes important and it dominates the action, then it will impact the triangulations that contribute mostly to the path integral when such scalar fields are present. And indeed, we observe this for the single scalar field, that for small delta, there's no change. It behaves more or less in the same way as if there was no field. But for large delta, the matter part of the action dominates, and the total, we have the preferred configurations are those who are pinched to a very small volume in some region. And now to visualize triangulations and field configurations, we now will reintroduce classical scalar fields. That's maybe technical detail. So we will assign the value of those four fields, phi x and up to phi t, to each four simplex. So we can think of the field as living in the center of a simplex. We have these four fields. Phi x winds around the target space when we go along the x direction. And on the next plots or images, a single pixel will denote a single four simplex. And dense regions will form fibers, and they will correspond to evolving outgrowths that I have shown on one of the first slides. So we start with three dynamical scalar fields that wind in the spatial directions. This is a projection only on the phi t field, which we introduce as a classical field only for the purpose of visualization. And on the y-axis, we have phi x. And here the circumference is 0, but you can think of it as a very small circumference. So the field is allowed to fluctuate still. So there is still the effect of quantum fluctuation of the field on the geometry, but this is basically negligible. And this plot here looks very similar for if you take just a typical configuration without any dynamical scalar fields. You can always introduce the classical scalar fields on top of an existing triangulation only to visualize it. So we see here there are some fibers with some elongation in time, and they denotes an outgrowth that also evolves in time. And now let's see what happens when we change this delta parameter, the circumference of the target circle for the scalar field. And we see that dense regions start to form. And we can expect, observing my previous results for a single scalar field, that it will localize, it will pinch in this direction where it winds. So phi x, for example, is one of the directions. And it should localize for some value. And this is indeed what happens. When I increase the delta parameter, the simplices using the coordinates defined by those scalar fields, they tend to localize or condense around some value. But what's, and this we explained already earlier. What's maybe more strange is that once you cross some value, it also, the volume profile start to change. Now, we don't have a field that winds in the t direction, but the volume profile measured in the time direction does change. And it then collapses to a single point in the field coordinates, which means that we have one large outgrow because one large outgrow will be visible as a very dense cloud of points. So if we look at the region where this change happens in the volume profile, it is now given by a cosine cube function. So here again, it's a volume profile on this axis. T is the original time foliation, and the volume profile, the average volume profile, behaves like a cosine cube function. Previously, we had a cosine function. Here we have a cosine cube function, which is exactly this what we observe also for a spherical spatial topology. So let me repeat that here, the topology of the triangulation or of the spacetime is toroidal. Both of the first topology of a space is T3, but we get a behavior typical for a spherical spatial topology, and we can also explain it using the mini superspace model. So first we observe, as I have shown before, that if you introduce a scalar field that winds in a given direction, there is a pinching in this direction. So like we start with the torus, but there is a pinching, let's say, at the end of the torus, and it effectively becomes a sphere. Of course, exactly by construction in our numerical simulations, it is a torus, but effectively the bulk of the volume is like has a topology of a sphere, it's spherical, and it starts as single slice starts to look like that. That there is a small area which with the genus with the hole, and the bulk of the volume is in the looks like a sphere. And we know that if the topology of the space is spherical, we have a curvature term, and this explains this bubble-like behavior and this cosine third function. So that the procedure or the effect is twofold. First, there's a pinching in the direction where the scalar field winds, and then the effective change of the topology of space enforces this blob behavior. Okay, so I should finish now. I will just say that we have shown that introducing dynamical scalar fields, it changes an effective topology of space and also space-time, depending on the delta parameter, which is the circumference of the target space of the field. Thank you.
Thank you very much. Questions? So maybe a short question. What is the crucial difference with these holes? So ball and donut or brezel, how would that? What's
the difference on this plot? Well, that the region where you have this hole is now much smaller, and the main volume, if you subtract or cut it out, then the main volume will be like a sphere with a pinch only.
Okay, so let's thank the speaker again.